Okay, hello everyone. I'm Maxime Vincent and I'm presenting to you the PicoTCP stack, which we want to present here as the uh, okay as the reference TCP/IP stack for the Internet of Things. Going to try to fix that first. That should be better. All right, we're good to go. So first, let me do some shameless publicity for the company I'm working for. It's called TAS. We are a leading embedded technology company. We're located in Leuven and Ghent. And what we're doing is we're providing consultancy training. We're doing projects together with our customers and doing outsourced services. What we want to do is ensure that our clients in co-creation with us can launch innovative and better quality products in a shorter time to market. But another important point is that we believe that connected devices are going to improve the quality of our lives in an innovative way. So that is why we have made this. PicoTCP, it's a fully featured and highly portable TCP/IP stack. It's designed really for small footprint embedded systems. So we're targeting the lower end microcontrollers here up until bigger targets. So why should we be the reference TCP/IP stack for the Internet of Things? That is because we have 4 areas which we focused on during the development of PicoTCP, and that is modularity, portability, performance, and quality. And I'm going to tell you about all these 4 focus areas a little more in detail. First, important for this conference, I think, is that that our software is free, as in free speech. So we have a dual licensing policy in place. Firstly, release the PicoTCP stack under the GNU GPL version 2. But then for the customers who are not really very happy with this kind of licensing, we also have a proprietary licensing possible because we are the full copyright owner of PicoTCP. Yes. It is V2 only. The question was, is that V2 only or V2 and later? No, we're sticking to GPL V2. So what does the stack look like? This is the first point, modularity. We've built up the stack from the beginning as a very modular stack because that's important for small embedded targets. There's one big bubble in the middle, which is the gray PicoTCP core. That one, of course, is mandatory, but all the other modules around it are optional, and you can choose whether you want to compile them in or not. Of course, there's some dependencies between them, but that's logical, I think. Then just to give you an idea of how big the stack is in terms of flash memory, we try to compile the complete stack with for an ARM target, which is the mbed board in this case. We compiled all the options in, and then we get somewhere around 68 kilobytes for all the modules you can see here. We think that's pretty small. Then let's see how we can build this up in a modular way. So we removed everything except TCP, UDP, and then we want to use only IPv4 because we're also implementing IPv6, and both can be used at the same time. When we built this full host mode config, we are somewhere around 30 kilobytes of flash. So how does it work? You select the bubbles, the modules, and you can do this just with a simple make command. To see all the available modules, just have a look inside our make file. I made the command I used here for the 30 kilobyte version of the stack, which I have just showed you. I have explicitly mentioned all the modules. If you don't mention any of them, you will just get all the modules. And then for the small lib size, I've also stripped the module here to see what it will finally take in your flash. But you shouldn't do that if you still want to link the library. Next point is portability. We we thought of portability since the beginning, so we are really CPU architecture independent. We run on 8-bit cores, on 16, on 32-bit, 64-bit, little or big endian. We have also thought of the smaller systems which have no operating system at all, so bare metal, small operating systems or schedulers, things like FreeRTOS, real operating systems or more complete operating system up until real-time operating systems. Right now, at this moment, we have about 10 or more different platforms which we already support, and we believe that it's very easy to port PicoTCP to a new board, and I will show you this in a minute how it's done. New operating systems should also be easy to support because we wrote our own operating system abstraction layer, so you should just implement this layer and all the rest stays the same. To show you a few of the architectures we support, 64-bit is not mentioned because we only tested this on POSIX client, so on basically on a Linux machine, because we don't have any 64-bit embedded targets at our place. But then in 32-bit there's really a lot of ARM variants, and I think almost every month there's a new one being introduced. It's really easy to port. So we have a few LPC chips, Cortex M0, M3, M4, a lot of STM32 variants also. On the 16-bit side, we have the MSP, low power microcontroller from TI. Also the PIC24F, which I will demo here later on. This is a target with really small resources. It has only 16 kilobytes of RAM, and we're running a complete stack inside of that. And then we even have one 8-bit target, so that's 80 mega 128, which is doing painless TCP IP communication. More portability even, so the communication chips. We support this set of communication channels. We have Wi-Fi chips running, we have Ethernet, we have USB CDC drivers, and then a bunch of virtual drivers which we use a lot during development or testing on Linux, for example. So we have TUNTAP drivers, VDE, and libpcap, which Wireshark is also using. Then the different operating systems which we can run on. At this moment, we use a lot of bare metal targets, so there's no operating system running, so all the calls are non-blocking. Then FreeRTOS is an operating system which is popping up a lot on the small devices. Of course, we have the Mbed RTOS, which is CMSIS RTOS compliant, so other CMSIS variants should work painlessly as well. And then we do a lot of testing on Linux and other POSIX targets as well. So what does our OS abstraction layer do exactly? We have abstraction from the mutexes and the signals, which are used for synchronization between the threads. Then the threads themselves or the processes are abstracted, and we have a BSD blocking socket interface. Now let's talk about the performance. These tests have been run on the Mbed LPC 1768, I think. That's a target running at 100 megahertz. We get a throughput for transmission of about 10 megabits and downstream about 20 megabits, which is not bad for an embedded target, I think. Then the CPU time here is stated in an amount of microseconds per loop, because our stack has a stack tick, and you can really choose yourself how many stack ticks or the period of one tick. So in idle state we have only 45 microseconds, and then at the maximum throughput, which was here the 10 megabits or the 20 megabits, we have something like 800 microseconds per tick. Then the RAM is something we're proud of also. The dynamic memory during these tests was maximum 8 kilobytes of memory, and on average around 4 kilobytes. The static memory here is the biggest one. It's 16 kilobytes, and that's actually just because we're allocating a lot of buffer, statically allocating a lot of buffer for the driver, so that we can buffer more incoming packets at once. You could also reduce that, but then your throughput goes down a little bit, so it's a trade-off you should make. But you can get these figures even lower. In the stack, 2 kilobytes, and on this pick target, we're even below 1 kilobyte of stack. Quality is something we're constantly focusing on, so the way we develop the stack is in an agile way, using Scrum, and we do test-driven development, so we make the test beforehand and then we implement the code which should make these tests green. We're also having continuous integration and automated testing, so whenever something breaks we get a big red screen and everyone should jump on the problem to get this up and running as quickly as possible. At the right you can see a kind of eco label, but then for code quality. This is a tool we're using, it's called TOBTIX, and it gives you an idea if you're writing decent code or not. The first time we run this tool, I think we were somewhere around an E, and so this gives you a constant reminder of write good code, document it, don't make it too complex, write unit tests and things like that. So we're planning on getting even higher, hopefully. So at the bottom you see a big list of RFC standards. That's not intended to be readable, but just to show you how many standards we comply to. And we tend to take these standards pretty literal, so we don't make any loose implementations of these, like some other stacks do. We are also community driven, so we're on GitHub. Please visit us there. You're free to file any bug you can find. As I said before, we are GPL v2 licensed, so use our stack, fork it, do whatever you want with it, as long as you stick to the GPL. We're also on OLO, which does analysis of open source projects, and there they're saying about PicoTCP that we have a young but established code base. We started first time on GitHub. First commit was around October 2012, and we have a large development team. We have stable year-over-year commits, so we're constantly working on this thing, and we're trying to make it better every day. So now, more concrete or more interesting is how to port this actually to a new platform. That's easy. You need just 3 things. That's memory management, which often isn't a big problem, so you just grab the malloc and the free functions from your C library. You need a few timing functions, just 2 actually, and then a driver for your hardware to get the packets really on your physical interface. So how do we do this? Memory management also is already said that you can use the malloc and the free functions from your C library if they are decent enough, if they are available. If you're using an operating system, then you could use the memory allocation from the operating system. And we're also right now implementing our own memory manager, because we believe that we can allocate and free memory more efficient than most C libraries do. Also coping with fragmentation when transmitting small packets and things like that. So that's a new development that's on its way. I think it almost made its way into the stable. There is an active pull request. Great. So next thing you need is timing functions. The way we set this up is a timer interrupt, which will every millisecond increment a 64-bit integer, so that we get a big enough time base. And then you need 2 functions, PicoTimeMS and PicoTime, which will return the elapsed time in milliseconds or in seconds. So how do we do this? This is an example from the embed implementation, I think, again. So the PicoZalloc is actually the wrapper around the malloc function which we'll use. So here you can see that it simply uses the malloc from the C library, and a requirement for PicoTCP is that you really zero all the memory explicitly. So if your C library doesn't do it, or you could have a calloc available, for example. Next thing is the PicoTimeMS. We're doing a trick here with a 32-bit integer, which is being incremented because it's a little bit faster, and then we're detecting when it overflows. And the PicoTime is just returning the same value divided by 1000. The last statement here is optional. You could use that as a a blocking function would just wait until another millisecond has elapsed. But it's not mandatory. Now we get down to the device driver. This API, we tend to make it very generic and very simple also. So there's only a few things needed. That's the PicoDev create, which will return a struct to a Pico device. And then you have its opposite at the bottom, which is PicoDev destroy, which will do all the cleanup. And then you have a send function and a poll function. So you want to transmit a packet, or you want to see if there's new data available or not on your physical interface. So the header is really simple. There's only two functions exposed, which are the embed create and the embed destroy in this case. All the rest is underneath, which you can see here. So this is the create function, which will allocate some memory at the top for the device driver. Then we will set the MAC address because this is an Ethernet device. Okay. We will init the device and then set a few function pointers which will do the actual work. These are callbacks which are put into a struct. Actually, what we've done here and what is a way that's easy to get started on new platforms is you make wrappers around the existing driver or implementation. In the embed system, we had Ethernet read available. So this is actually just a wrapper around this function, and then you can get started with a one-page function or even a half-page function, and PicoTCP driver is working. The send function is just the same story. We're using the Ethernet write and Ethernet send API from the embed. So let's get down to a demo. What we've done here is we've taken this is a small MIDI keyboard. Actually, it's meant as a toy for the Wii, I think, but it wasn't a great success, so you can find them really cheap on eBay. The great thing is they have a MIDI port, which we will use. This MIDI port, the MIDI protocol is really simple, so you just need a level translator, and then with a UART you can read out bytes which are on the MIDI channel. And what we're doing is, you can see this here, is we take the keyboard, we translate this to a serial stream. The microchip PIC controller will read this out, use PicoTCP to put this on a Wi-Fi channel. Over the Wi-Fi we are actually transmitting a TCP stream with on top 0MQ, which is a great message queuing protocol, which makes it really easy to send and publish messages actually. So the keyboard here is a publisher, and my laptop will subscribe to this publisher and get every message that it makes available. So these messages will be the MIDI notes which are played on the keyboard. Then I can receive them with a tiny Python script on my laptop. And then I put these bytes again into a virtual MIDI device, and this virtual MIDI device can then be hooked up to any synthesizer on my laptop. So I can show you the Python script which will read these binary packages. So that's about it. I think there's a few more lines at the bottom. Most of them are print functions just to see what's going on. So this is just to show how easy it is to do TCP/IP communication by using 0MQ. Yeah, I will just power up the device meanwhile and let it connect to the Wi-Fi network. And I don't know if there is anybody here who can actually play the piano, because I can't. So that we can do this demo. Is there anyone who wants to play a few notes? Yeah, come along. Yeah, except that. Yeah, the board is it's USB powered indeed. So the board is connected. I will now connect the Python script, and you can see that it's immediately receiving MIDI messages. And now I have this virtual MIDI device, and I should connect it to to a synthesizer. And now you should be able to play the piano. Maybe. Yeah, go on. Oh. Yes. Let's see. I'll make the connection again. Okay, go ahead. Great song. Thanks. So I don't know if there's any time left for 2 minutes, 2 questions. Yes.
So this is a great project. I'm very impressed, and I'd like to use it, but my project's GPL v3, so I can't. Why have you done that? Why do you think that's a good idea?
That's a good question. We think the v3 is a little bit too restrictive for the purpose. Yeah, it's true. I don't know. Maybe I can call the help of an expert on this matter.
I would reply with another question actually. So what was the need exactly of the GPL3 if we already had the 2, which was working pretty well? I think we can take this offline.
Okay, so we're going to cut this discussion about GPL licensing. I think if you simply say GPL2 or later, and then I think the problem is solved. But we can discuss this later. Thank you very much for the demo. If anybody wants to carry on playing the piano, we have an open slots after the next speech, but we're going to stick to our timing here. Thank you very much for this amazing piece of work. Awesome. We have a 5-minute break, and then we have our last formal talk for the day.